semester. So I'll just introduce this problem. We will come back to this at the end of the class, at the end of this presentation. A thief uses a can of sand. We're looking at problem 113. A thief uses a can of sand to replace a solid gold cylinder that sits on a weight-sensitive alarmed pedestal. The can of sand and the gold cylinder have exactly the same dimensions. So if we look at this, they give us the dimensions. This is an example of dimensional analysis if you're guessing or figuring out what we're about to do. Dimensional analysis in terms of length. So length is 22 centimeters, radius is 3.8 centimeters. Calculate the mass of each cylinder. Ignore the mass of the can itself. So we're looking at the mass of the cylinder, given that we have the density of the gold and we have the density of the sand. Then they also ask this question: did the thief set off the alarm? Explain. So let's read this problem one more time and then we'll come back to it at the end of this presentation. A thief uses a can of sand to replace a solid gold cylinder that sits on a weight-sensitive alarmed pedestal. The can of sand and the gold cylinder have exactly the same dimensions. Length is 22 centimeters, radius is 3.8 centimeters. Calculate the mass of each cylinder. Ignore the mass of the can itself. Density of gold is 9.3 grams per cubic centimeter. Density of sand is 3.00 grams per cubic centimeters. Did the thief set off the alarm? Explain. So just keep that problem in your mind. You could let's let it loom around in your mind, and let's begin the lecture for today. Okay. So what is chemistry? We discussed this earlier. Chemistry is basically the science of substantial change. And you look at those changes in terms of different units, the compositional units, whether it be atoms, electrons, quarks, whatever the case may be. We look at the change of the substance in its terms of its compositional units, or in terms of the macroscopic object itself. What is matter? Matter is anything that has mass and takes up space or has a definite volume. What are the properties of matter? Matter's properties, they depend on the physical state of that matter that we're looking at, whether it be solid, liquid, gas, or plasma. What are some units of measurement? Some units of measurement are SI units, of course, and they could be ranged from length to Celsius, depending on what you're looking at. What is dimensional analysis? It's a way we do calculations. So, and I've already discussed these things. So we've discussed all of these things in lecture already. The atomic theory of matter refers to John Dalton's atomic theory. If you want more information about that, you feel free to look back in your textbook or re-listen to the lecture. We'll discuss a little bit of that later on. Discovery of atomic structure, the big players who were in that or who functioned in that were J.J. Thomson. He gives an idea of the electron. Ernest Rutherford told us all of the charges posit, and all the positive charges posit in the nucleus. And also, we had Ernest Rutherford, J.J. Thomson, and James Chadwick who gave us an idea of his work led to the discovery of the proton. Now, the modern view of atomic structure came from players such as Bohr. And his work was further extended, when he was like the first relay runner, if you were to think of this as a race. Bohr, and there were other scientists who came behind and gave us further insight into atomic structure, including those who I just previously mentioned. Atomic weights. Now we get these things, get these values from the periodic table. Atomic weights, we get that information from the periodic table. The periodic table, that's a system of elements or a group of elements arranged based on the atomic numbers, and we get an understanding of that, or we understand what the periodic table is saying through the use of looking at the atomic numbers, looking at the mass numbers, knowing which group is which. So for example, knowing which group is which, there we go, we get it. And we look at that in the next slide. Molecules and molecular compounds. So this is something, a nuance I want to make sure I explain well. A molecule is anything that has more than one atom. A substance that has more than one atom. A compound is different from a molecule, or it's a type of molecule in that you have two atoms, but they're different. Molecule, you just have two atoms, more than one atom. Compound, you have more than one atom, and those atoms are different. So that's different. Remember that. Ions and ionic compounds. So ions, we could range from cations to anions. Cations have lost an electron or several electrons and have a positive charge. Ionic compounds, for example, sodium chloride, salt, is made up of, if you look at the Born-Haber process in which you form those things, you have the formation of sodium cations and chloride anions coming together to form the crystalline lattice. So an ionic compound, an example of that is sodium chloride. The naming of those ionic compounds, it depends on the type of compound you have. If it's binary, so if you have two things together, two types of atoms together, two different atoms together, if you have two things together, if you have sodium and if you have chloride, sodium cation and chloride anion, those things coming together, that's going to be a binary compound. And typically when we're writing binary compounds, we write the name of the element that is to the left or to most to the left, or the alkali, the metal basically, the thing that has the most metallic character. We write that as first, the first thing. So sodium will go first. And then chloride, we write chlor, CHLOR, and then the suffix "ide" comes from the fact that it's an ion. So that's sodium chloride, and it's a binary ionic compound. Okay, simple organic compound naming, those come into play depending on the types of number of carbon atoms that you have. So let's just do a quick survey of the periodic table. So over here we have our alkali metals, alkali earth metals. We have our transition metals here. Then we also have metalloids, bic gas, antipo, boron, silicon, germanium, arsenic, antimony, tellurium, polonium. We have aluminum, these are group 3. We have carbon, all of the big players. We have our halogens, and then we also have our noble gases. So key things to keep in mind. The group number gives us an idea of the valency. So the group number gives us an idea, especially for main group elements. Groups 1, 2, 3, 4, 5, 6, 7, 8. In ideal situations, those group numbers give us the idea of the valency. Noble gases, it just tells us it has a complete octet, so they're extremely stable in their ground state. So group 1 will typically have a positive charge, or they will form cations with a +1 positive charge. The group 2 elements will form a cation with a +2 positive charge. Group 3, for example, aluminum, forms a cation with a +3. Silicon has various valencies. Germanium, tin could be 2+ or 4+. So 4, but this is consistent with the idea that they have the capacity to form or to have the valency of 4. Nitrogen, now as we go from group 5 onward, these atoms or these elements are electronegative. And for example, with nitrogen forms a anion N3-. So we went from the things that were donating or giving away the electrons, groups 1 through 4 basically, to those that are accepting electrons. So nitrogen is accepting electrons, and it typically forms N3-. Oxygen accepts 2 electrons, O2-. Fluorine accepts 1 electron, F-. And that typically is consistent throughout the group. So that's what the group numbers tell us. Now the period numbers tell us the number of electron shells. And this coincides well with the Bohr model as we draw those models out. As well as there's some things for you to note. Let me get my annotating option. This right here is known as the S block. This right here is known as the P block. This right here is known as the D block. And this right here is known as the F block. So I'm just exposing you to that content now so that you're familiar with it before we go into it in depth. Those letters, they come from quantum chemistry, and they give us an idea of how the electrons are distributed typically within the atom. So they just give us an idea of that, and that's all I'll say about that for now. Now the F block, we have our lanthanides and actinide series, and those we you just be aware of them for now. Let me erase this. Let me see. Let me erase this. There we go. Okay. So common cations. These are common cations to think about. Hydrogen typically forms a positive one. Cation that's consistent with what we see in the periodic table. So, yeah. Lithium, sodium, potassium, cesium, and silver form +1 cations. Magnesium, calcium, strontium, barium, zinc, cadmium form 2+. Aluminum forms 3+. Ammonium forms a +1. Now we're talking right now. Ammonium is a compound. It has two different elements, two different atoms that come from one from nitrogen, one from hydrogen. Actually, one from nitrogen and four from hydrogen. But at the end of the day, it's made up of two different elements, nitrogen and hydrogen. So copper +1, cobalt 2+, copper 2+. Copper can have copper is a little different because when you look at our transition metals, these ones are special. Copper is special. Copper is special. Chromium is special. Manganese is special. Iron is special because they have various valencies. So if you're familiar with what you did in GCSE chemistry or earlier chemistry, in which you would discuss something as ferrous hydroxide or ferric hydroxide, ferrous +1, ferric +2. So those things you want to keep in mind. Those things you want to keep in mind. Copper, cuprous 1, cupric 2. Just want to keep those things in mind. Okay. So you have your mercurous. These are just classic examples of what I'm saying. It's important to be well versed in this language, so as we progress throughout the semester, you're aware of what I'm talking about. So as we continue on, we see that we have hydride. Yes, in this case, you have a hydrogen that has a negative charge. That's just an example of how things are not set in stone, how hydrides form. You typically see hydrides forming or hydrides being released when you have a basic reaction, or some type of nucleophile. So fluorides, chlorides, bromide, iodide, all of those anions, they gained electron density. Oxides, peroxides, sulfides, all of these gain 2 electrons. Nitrite, this is consistent with what I said, gain 3 electrons. Acetate, chlorate, perchlorate. Now these right here, chlorate, perchlorate, nitrate, and permanganate. These are an example of what we call polyatomic anions. If you listen to the name poly, more than one, atomic, more than one atom, ions, and that's what these are. Same thing with carbonate, chromate, dichromate, sulfate, phosphate. All of these, from this chlorate to phosphate, all of these are an example of polyatomic anions. Okay, so we discussed the naming of those things already. So these things we have discussed, the postulates of Dalton's atomic theory, we have discussed that already. Key experiments, we discussed that. Describe the structure of the atom, we discussed that. The electric charge, we discussed that. The chemical symbols, subatomic composition, that's a fundamental concept we will discuss. Atomic weights, we'll discuss that. Describe how elements are organized. These are all key skills that your book requires you to know. So if you look in the textbook that I recommended that you buy, that's a required textbook for this class. I sent you a link of in the email. These are skills that you will see. Distinguish between molecular and ionic substances in terms of their composition. We've done that. Distinguish between empirical formulas and molecular formulas. So empirical formulas, this is something we will discuss. Empirical formulas is the simplest representation of a chemical formula. Molecular formulas is just a general representation or the representation that you first get. Empirical is the simplest form of the chemical formula. Describe how molecular formulas and structural formulas are used to represent the compositions of molecules. Um, Structural formulas show you the shape, give you an idea of the molecule's geometry. Molecular formulas just give you an idea of what element it's made up of. Explain how ions are formed by the gain or loss of electrons, and be able to use the periodic table to predict the charges of ions. Explained already. All these things we will get to or we have already discussed. Now, balancing chemical equations. Now, this is a fundamental idea. I need you to go back and review that. If you don't remember how to balance chemical equations, I need you to go back and review that. That's going to be very important when we start discussing thermochemistry. Balancing chemical equations means you have the same number of elements on both sides of the arrow. Same number of element A and same number of element A on the reactant side, same number of element A on the product side. And what I mean by same number, same moles, same stoichiometric coefficient, same thing on the reactant side and same thing on the product side. It's consistent. If you don't remember it, go back and review it. Calculate molecular weights. That comes when you do your periodic table. Also, you can calculate molecular weights from percentage of relative atomic mass. You can calculate that from abundances and things like that. So convert grams to moles, moles to grams. That's stoichiometry. We've reviewed dimensional analysis. Go back and review the BGCSE stoichiometry things if you don't remember those. Avogadro's number and percent yield. So I'll just show you a quick example of how to do percent yield. Percent yield is done by your actual yield over your theoretical yield times 100 over 1. Actual yield over theoretical yield times 100 over 1. Now, your actual yield is the value that you get or you obtain in your experiment. The theoretical yield is the value that you calculate using dimensional analysis from the value, or the number of moles of the element that is the limiting reagent. Let me draw that back. So you have in your reaction a element or a molecule or a compound that will be consumed first. We'll run out of that one first. And that limits the reaction because it determines how much product you can make. So when you determine which element or which molecule or which compound is the limiting reagent, you use that value of that element and you calculate how much product you have as possible from the reaction, and that is your theoretical yield. In theory, that's what you should get. Okay, so let's keep going. Let's keep going. Okay. Okay, recognize compounds as acids or bases. Okay, metathesis, redox. Okay, so I'm gonna give some explanations for these things, but we will discuss these. We will discuss more of this in general chemistry too. But recognize compounds as acids or bases. So acids and bases the typical in the Bronsted-Lowry definition of acids and bases, an acid is something that releases hydrogen ions in solution, has a low pH. A base is something that basically accepts hydrogen ions, hydrogen positive cations. And actually, another way to put this is a base is something that accepts protons or accepts hydrogen ions. Strong, weak, or non-electrolytes. Strong acids completely ionized in solution. Weak acids partially ionized in solution. Non-electrolytes rarely or seldom ionized in solution. Recognize reactions as acid, base, precipitation, metathesis, or synthesis. or redox. Acid base, you have to know whether you have an acid and a base in the reaction. Precipitation, you have stuff with two aqueous reagents and you end up with a solid. Metathesis, that's a little bit advanced for this level, but it's the form of synthesis that's involved with transition metals. Redox, you have reduction and oxidation occurring at the same time. Be able to calculate moles or grams of substances in solution using molarity. That is a BGCSE skill. Go back and review it if you don't remember it. Understand how to carry out a dilution. That's something you'll learn in lab. Understand how to perform and interpret the results of the titration. That's something you'll learn in lab. So we discussed this already, and I showed you this video in the previous lecture. So let's go through this problem now. So I introduced this problem to you. Let's read it again. A thief uses a can of sand to replace a solid gold cylinder that sits on a weight-sensitive alarmed pedestal. The can of sand and the gold cylinder have exactly the same dimensions: length 22 centimeters and radius 3.8 centimeters. Calculate the mass of each cylinder. Ignore the mass of the can itself. Density of gold is 19.3 grams per cubic centimeter. Density of sand is 3.00 grams per cubic centimeter. Did the thief set off the alarm? Explain. So let's look. What are we given? We are given that the cylinder has dimensions: length 22 centimeters, radius is 3.8 centimeters. We are also given that the density of gold is 19.3 grams per cubic centimeter, and the density of sand is 3.00 grams per cubic centimeter. What are we solving for? See, this is the same heuristic that I gave you earlier. Given, solve for conceptual plan solution, check and see if it makes conceptual or chemical sense. So what are we solving for? We're solving for the mass of the gold, given the length, the radius, density of the gold. Technically, we're given the length and radius of the cylinder and density of the gold, and the mass of the sand, given the density of the sand. So what we're going to do, we're going to look at length and radius, and we're going to convert that to volume. Then we're going to look at density and volume and convert that to mass. Volume is equal to length times pi times r, or radius squared. Density is equal to mass over volume. So the volume of the gold is equal to the volume of the sand. That's the assumption that we're making in this equation, in this solution process, in solving this problem. And that's going to be 22 centimeters, which is the length, times pi, 3.14, times the radius, 3.8 centimeters squared. And that's going to be equal to 998.0212 cubic centimeters. And density is equal to mass over volume. So we rearrange the formula for density, and we get that mass is equal to density times volume. So we just solve for the volume, 998.0212 cubic centimeters, and then we multiply that volume by the density of gold, 19.3 grams per cubic centimeter, and then we get 1.926181 times 10 to the 4 grams. Or we do it to two significant figures, 1.9 times 10 to the 4 grams. The units are correct. The magnitude of the answer seems correct, considering the value of the density is approximately 20 grams per cubic centimeters. Two significant figures are allowed to reflect significant figures in 22 cubic centimeters and 3.8 cubic centimeters. Typically, we truncate the non-significant digits because the first non-significant digit is a 2. So given the values that we're given, all of our values have two sig figs, or we typically, actually that's 3, but we typically give our answer according to the value that has the lowest number of significant figures. So if we look at the values, and one of them has 2 sig figs, 3 sig figs, and then 2 sig figs, so we give our value 2 sig figs because of that. Okay, now let's look at the mass of the sand. We have the volume now that we multiplied by the density. We did the same thing we did to determine the mass of gold. We do to determine the mass of the sand. So 3.00 grams per cubic centimeter times 998.0212 cubic centimeters equals 2.99406 times 10 to the 3 grams. And that's equal to 3.0 times 10 to the 3 grams. The units are correct. The magnitude of the answer seems correct, considering the value of the density is 3 grams per cubic centimeter. This number is much lower than the gold mass. Two significant figures are allowed to reflect the significant figures in 22 and 3.8, which is exactly what I said. Round the last digit up because the first non-significant digit is a 9. So comparing the two values, now 1.9 times 10 to the 4 and 3.0 times 10 to the 3 shows a difference in rate of almost a factor of 10. This difference should be enough to trip up the alarm and alert the authorities to the presence of the thief. So from these calculations, we could theoretically reason out or rationalize whether the thief set off the alarm. Power of chemistry. Keep that in mind. All the best this semester we ahead help you grow and build intellectual capacity. So let's keep going. Let's keep going. So I'm going to go through, I'm going to help you out, and I'm going to go through some BGCSE chemistry concepts. I'm going to go through, I went through the curriculum and I designed another resource for you, resource that can be helpful for you, and we're going to go through this. Okay. Okay. Do reachable mode. There we go. So we discussed what chemistry is. It's a scientist change that can occur in the context and on the scale of substantial change of quarks, subatomic particles, or atoms. Now we're just going. This is a recap of BGCSE chemistry. I want you to be aware of what's going on in the class. So I'm going to give you a little bit of review of BGCSE chemistry during this lecture this morning. So focusing on BGCSE chemistry, there is organic chemistry, biochemistry, physical chemistry, and theoretical chemistry. And chemistry is basically all of those chemistry, not in a nutshell. We just do a surface level view of those things. So it's very basic chemistry. So organic chemistry is a study of hydrocarbons, focusing on their reactivity, structure, mechanism, and the theories associated with those reactions. So there are 5 key ideas that you were exposed to in BGCSE chemistry: chemistry fundamentals, the mole concept, acids and bases, energy and speed changes, and applications of other types of chemistry. A core idea that you were introduced to is that matter is made of particles ranging from atoms to ions. These particles are arranged differently in solids, liquids, and gases, and when heat or energy is applied, phase changes also can occur. So let's keep this in context. The particulate nature of matter is that matter is made up of particles. These particles range from atoms to molecules to ions. These particles can vibrate and move, and eventually the distances between the particles changes, and that affects the physical state, resulting in phase changes. So the elastic collisions are the consequence. Let's talk about elastic collisions, because this is tied into something you learned in BGCSE chemistry, or this is tied into the kinetic molecular theory, which is a very important concept to understand. So elastic collisions, which occur ideally with particles when they contact each other, and they result in the conservation of momentum, or that momentum is conserved. The final momentum is equal to the initial momentum. It's almost like two good basketballs hitting each other. The elastic collisions are the consequence of applied stress or energetic transfer from or between particles. Elastic collisions occur ideally between particles, and this is a consequence of kinetic molecular theory. Okay, so let's continue on. With that in mind, let's talk about temperature. Temperature can be expressed as the average kinetic energy of a group of particles, atoms, molecules, or ions at a physical state. Temperature can be related to kinetic molecular theory, energy, and motion. The previous statement is true, since kinetic energy increases occur at the same time with motion, and that ideally results in increases of thermal energy. So let's keep going. Diffusion, so these are all tenets of kinetic molecular theory. Diffusion can be explained as the movement of particles down a gradient without external input of energy, the opposite of active transport. This is a consequence of the kinetic molecular theory, in that particles are in constant rapid motion, interacting with elastic collisions. Diffusion is physical state and temperature dependent. Diffusion is the movement of particles from high concentration to low concentration, or basically down a concentration gradient. Diffusion is dependent on the physical state of the substance and the temperature at which the substance is at. Okay. So in fact, it is a fact that solids, liquids, and gases are made up of particles, and each phase has a different arrangement of particles. Solids are closely packed in structures that absorb vibration, shocks, and transfer heat uniformly. However, a liquid has more interparticle distance that allows for movement and transfer of energy. These are ideal situations. Also, gases have far greater distances between their particles. Phase changes that are with the physical states occur with the bonding arrangement of the substance. Phase changes, one more time, the phase changes that occur, uh, they occur while the bonding arrangement of the substance remain the same. So when you have a phase change, no intramolecular bonding has changed. Intermolecular bonding may have changed, but intramolecular bonding has not changed. Melting points and freezing points are pressure dependent and occur at a specific temperature and a specific pressure. Liquefaction and condensation are both phase transitions that occur between gas and liquid states. However, liquefaction involves direct transition from a gas to a liquid. However, condensation involves transition of a gas to a liquid or a vapor to a liquid. So condensation is like a wider reaching term. So we discussed these already. Now let's discuss some of these key players, big players in atomic theory. There were several key players in the development of atomic theory. First was Democritus. He provided the ideas associated with the substances being composed of atoms, and these ideas originated with Leucippus. Second was Dalton. He provided the historical and descriptive framework for atomism, noting ideas mentioned earlier. Add to this were Boltzmann, who provided a probability. Boltzmann, who provided probability framework for atomic kinetic energy. His work ultimately helped establish the relationship between kinetic energy and temperature, which relates as the average kinetic energy. After was Ernest Rutherford and his alpha particle gold foil experiment, which provided evidence that supported the existence of nucleons. Nucleons, you have your protons and neutrons, that's a nucleon. In the sense of nucleons. Nucleons are referring to your protons and neutrons, those things in the nucleus. Following this was the work which led to the confirmation of the existence of the subatomic particle, i.e., the electron. Moreover, was the work of James Chadwick. So following this was the work of J.J. Thomson, which led to the confirmation of the existence of the subatomic particle, the electron. So a nucleon could be a proton or a neutron. Moreover, was the work of James Chadwick, whose work helped confirm the existence of the proton. Along with these pioneers was the work of Niels Bohr and his model we will discuss this semester, from which we obtained the Bohr model. Additionally, it is noted that Gilbert and Lewis aided in providing a noting system for electrons and their atoms, which as time progressed, added to the toolkit of organic chemists in describing mechanisms. However, it is established that the position and momentum of an electron cannot be determined with equal accuracy, and that's the Heisenberg uncertainty principle. So these things are foundational. I'm not going into all of that. Feel free to go over your BGCSE notes. Feel free to go over your BGCSE notes. see. Okay. Let's actually, you know what? Let's just go over these things and go over the concepts, the foundational parts that occurred in the BGCSE curriculum that are very relevant to what we'll discuss this semester. A bond is an attractive force between nucleons and electrons. Nucleons can be protons or neutrons. Bonds can be dative, in which the pair of electrons come from one element, or covalent or ionic. Covalent bonds occur between nonmetals. Ionic bonds occur between nonmetals and metals. The ionic bond occurs between metals and nonmetals. For example, potassium chloride and cesium chloride. Also, the covalent bond occurs between nonmetals. So ionic bond occurs between metals and nonmetals. Covalent bonds occur between nonmetals. Carbon monoxide, a product of incomplete combustion, has covalent bonds, and dinitrogen monoxide, N2O, laughing gas, has covalent bonds. Bonding exists on a spectrum, but for the BGCSE, bonds were set categories, especially covalent bonds. But in reality, covalent bonds exist on a spectrum in which you could have polar covalent or non-polar covalent bonds. So this is an example of a Lewis structure. You can draw an example of of metallic bonding. Now let's talk about the concept of the mole involves a chemistry analog of the dozen. So it's almost like describing, to say something, a mole of something is almost like saying a dozen of something. But numerically they're not the same. But what you're trying to do is name a group of items or a number of items using one word. So a mole means you have 6.02 times 10 to the 23 somethings, or particles, or atoms, or whatever the unit that you're looking at, unit of substance that you're looking at. This is typically how you did your stoichiometry calculations. Given mass of reactant over 1 times 1 molar of over the mass of the element times the molar ratio times elemental mass of product over 1, and then you get your mass of your product. Molar mass is the mass of 1 mole of a compound. It is important since it is used in dimensional analysis and stoichiometric calculations. Also, the empirical formula is the simplest representation of a molecule or compound, and the molecular formula is a common representation of a molecule. Given mass times 1 mole over molar mass gives you the designated number of moles. The number of moles, designated number of moles over the lowest number of moles equals empirical formula. Molecular formula is given mass over empirical formula mass, and that gives you a scale factor. The scale factor times the empirical formula gives you your molecular formula. It's important to remember that 1 mole of a gas is RTP versus STP. RTP 24 liters per mole. That's standard. That's the standard RTP, room temperature and pressure, in which you have 20. This is the volume a gas occupies. The RTP 24 liters per mole. Temperature is going to be 0 degrees Celsius. Pressure is going to be 1 atmosphere. Standard temperature is 25 degrees Celsius. Standard pressure 1 atmosphere, and standard temperature and pressure, the gas occupies 22.4 liters per mole in terms of volume. Okay, so Dmitry Mendeleev, what did he do? He helped organize the table, and from this organization of the table of elements, he organized it into periods. We know that the period number refers to the number of electron shells, and the group number, top of the columns, refers to the valency of the elements in the respective column. Okay, in the table you have 9 big ideas. Group 1 is alkali metals like lithium. Group 2 is alkaline earth metals like magnesium. The middle section of the table is transition metals, followed by group 3, 4, 5, 6, which are elements with different properties. Group 7 is halogens like fluorine. Also group 8, also known as group 0, is noble gases. A note on solubility. Now we could go into all of this, but this is not completely relevant to what y'all will be doing this semester, so we will not discuss it. The valency of an element is the amount of electrons an atom will lose, gain, or share in order to become stable and achieve a ground state noble gas configuration. This idea is important because it is the basis of chemical reactivity and it influences the formation of bonds. It has relevant senses in the periodic table. It can be obtained from the four main group elements and the group number. So when you're writing formulas for ionic compounds or for polyatomic ions or ionic compounds, consider these general rules. Write the symbol, write the valency, exchange the valency for notation purposes, and write the formula with the exchange valency as the subscript. Extra information on naming and radicals. Naming varies depending on the class of compounds. For example, ionic compounds versus organic compound. You also have radicals, which are atoms with unpaired electrons, for example, a chloride radical. We're not going into all of that. That's for organic chemistry, in which you have singlet, doublet, or triplet. But we're not talking about that. We're not talking about that type of notation, radical notation. But let's get back to what's relevant to us. You have your conservation laws, and important to know those. You have the different definitions, and I hinted at this when I started introducing acid-base ideas. You have, for the BGCSE, the most common definition was the Arrhenius definition, in which you have a base acid producing hydrogen ions in water and a base producing hydroxide ions in water. However, for many things, even in organic chemistry, we tend to look at the Bronsted-Dory definition, in which an acid produces protons and a base accepts protons. There's also the Lewis definition that you will also look at in organic chemistry, which states that the acid accepts electrons and the base releases electrons. However, as stated earlier, the Arrhenius definitions were used in high school. Bronsted would typically be used in general chemistry, and Lewis definition and Bronsted would be used in organic chemistry. The strength of an acid or base is directly proportional to how much of it ionizes in solution. The strength can be measured using the pH scale, which is a logarithmic scale. Acids tend to have approximately low pH values. Neutral occurs, so low pH values 0 to 6.5. Neutral occurs at 6.9 to 7.5, and basic is from 7.5 to 14. These are approximate ranges. In terms of indicators and neutralization reactions, this stuff, it's relevant, but not relevant to you all this semester. Later on, we will discuss these things. If you take general chemistry 2, you'll discuss this acid-base theory in more detail. Okay. Le Chatelier's principle. That's for general chemistry 2. General chemistry 2. Okay. All the things. General chemistry 2. Okay.